Dear students, in this video you will learn about sudden loss of one of the parallel lines, sudden short circuit in one of the parallel lines. So, in this we have two cases: short circuit at one end of a line, short circuit away from line ends. So, these two concepts we will discuss in this video. First, we will see sudden loss of one of the parallel lines. Here we are considering two lines connected between generator and infinite bus. So, here we have a two lines. So, you can see in this figure 1, figure 6.32. So, one line suddenly disconnected, sudden loss of one of the parallel line. So, one line is disconnected in these two. What will be the system position? What will be the power system? What will be the power? What will be the voltage? So, let us consider. So, single mission, single generator is connected, infinite bus through two parallel lines. So, two parallel lines are connected between generator and infinite bus. The stanchion stability, due to the stanchion stability of the system, one of the line suddenly switched off. One of the line suddenly switched off. That means, so suddenly one of the circuit breaker is turned off, circuit breaker is disconnected. So, while operating steady load conditions, so when the steady load conditions, one of the line is disconnected, we will get a instability of the system. Okay. So, here first case, before switching off the power angle equation is, before disconnecting the one of the line, what will be the power angle equation? So, PE1 is equal to modulus of VE modulus of V by XS plus X1 parallel X2 into sin delta. So, you can say that PM1 sin delta curve 1, and second case is one line is switched off, line 2. So, in this two lines, line 2 is we are switching off. What will be the power angle equation? So, it is similar to the previous one. PE2 is equal to PE2 we are considering modulus of V into modulus of V by XS plus X1 into sin delta, that is equal to PM2 into sin delta. So, that is a curve 2. So, here we are considering two conditions. One is before switching off the line, after switching off the line. So, here we can also see the second diagram. So, line is having reactances X1 and X2. So, reactance diagram, single line reactance diagram you can also see in this figure. Xs is the synchronous mission reactance, X1 and X2 are the line reactances. So, when two curves, so curve 1 before line is switched off, so line is switched on and switched off, curve 2 represents the switched off conditions. You can observe clearly in this graph. When PM2 is less than PM1 as Xs plus X1 greater than Xs plus X1 parallel to X2. So, reactances and powers you can observe here, power is less and reactance is more. So, as soon as line 2 was switched off, the original operating point on the curve 1 is shifted to the point B. So, immediately if line 2 is switched off, what will happen? The curve will be shifted to a point B on curve 2. So, here we can see. So, curve 2 and curve 1 points how it is shifting here, right. Accelerating energy corresponding to area 1 is put into rotor followed by deaccelerating energy. So, once suddenly switched off, what will happen? Rotor will get a deaccelerate. In an area A2 equal to A1 is found above the PS line. So, above the PS line you can find. The system will be stable, and finally operates at C corresponding to a new rotor angle delta 1 greater than delta naught. So, here we can see delta 1 and delta 2. So, here what we can say is before earlier we are considering only one curve, now we are considering two curves. Since one line we are switching, so one line we are disconnecting, on one line only we are operating. So, two lines, two infinite bus, two lines are connected between infinite bus and power generator. So, one line is disconnected, what will be the power variations in the power system? So, here curve 1 represents the two lines are operating, and curve 1, so second curve represents the when the power is shut down. So, when the power is more due to so when the power is decreased due to one of the line is disconnected. So, here you can see line 2 is switched off. So, here when the line 2 is switched off, the curve 1 is shifted to point B. So, it will decrease. So, A to B it will decrease. So, when before switched off, the curve is operating at A point. So, when switched off, one line is disconnected, it will shift it to point B. So, for the limiting case of stability, delta 2 as a maximum value delta m. So, delta m, maximum value delta m is 180 minus delta 1. So, here we can see the 180 and delta 1. So, which is the same condition as the previous example. So, in previous example we have seen, right, only one line. So, it is similar to that, right. So, here we can see sudden short circuit in one of the parallel lines. So, before what we have discussed, one line is disconnected, now one line is short circuited. So, short circuit at one end of the line. So, where it is short circuited? One end of the line. So, let us assume that three phase short circuit occurs at one end of line 2 of a double circuit line as shown in figure. So, here we have two lines, one line becomes short circuit. So, in this case you can see the reactance diagrams. So, we reactance diagrams, the equivalent reactance diagrams before, during and after fault clearance. So, here we can see before, during, after fault. So, before fault, after clearing the fault. So, before fault xs, x1 and x2 will be there, and during the fault, so one line will be short circuited between the two reactances x1 parallel to x2 and xs. Once after the fault, so x2 will be disconnected. So, before the occurrence of the fault, the power angle curve is as given by PE1. So, modulus of E by xs plus x1 parallel to x2 sin into sin delta, PM1 into sin delta, and during the fault, so during the fault PE will be equal to 0. So, upon occurs of the three phase fault at the end of line 2, there is no power flow. So, PE2 is equal to 0. The circuit breaker at the two ends of the faulted line open at the T1 called the clearing time. So, disconnecting the faulted line, the power flow is now restored via the healthy line 1 with the power angle curve is given as so here we can see the after clearing the time, PE3 is equal to modulus of E into modulus of V by xs plus x1. Since x2 will be disconnected, so what is the difference between these two is, here before occurrence of the fault x2 will be there, x2 will be considered. So, after the fault x2 is disconnected, x2 is not there in this equation. Since in previous slide we have seen reactance diagrams, x1 and x2 will be there before the fault. After the fault what will happen, x2 is disconnected, x2 will be not there. So, that is what x2 is not there. So, that is the differences between these two cases. So, here Pm3 into sin delta you will get. So, this is differences during fault, after fault. So, obviously Pm3 will be less than Pm1. So, here we can see Pm1 and Pm3 curves. So, here Pm3 magnitude is less than Pm1. The rotor now starts decelerate. So, rotor speed will be decreases, the system will be stable. If a decelerating area A2 can be found equal to accelerating area A1 before delta reaches the maximum allowable value delta m, It easily follows that larger initial loading Ps increases del A1 a given clearing angle delta 1, and therefore quicker fault clearing would be needed to maintain stable operation. So, here we can see before fault, after fault, during fault curves you can see. So, before fault maximum power we are getting, after the fault it will decreases, and during the fault also it will be decreases. So, this is about variations of different powers due to sudden loss of wire, sudden loss of and sudden loss of line and short circuit of the line. So, in next video we will see short circuit away from line ends. So, this topic we will discuss in next video. Okay. Thank you everyone.